So I cut a piece of cheese and cut myself. I don't want any of my kids to have any problems in life. Yeah, good for you. Oh. All right, folks, everybody settle down, please. All the usual caveats, laptop shut, name tags out. I don't know who you are, Lakshay. Please have your name tag out. So, you're supposed to write beta. You're supposed to write beta too. No, you're not alpha. Shows alpha. All right. So let's start, guys. Can you hear me? Today we actually have, this week we have a pair of guest lectures that I haven't informed you about. So over in 18786, Ashwin's got someone doing 2 lectures on learning representations. These are very good lectures. Unfortunately, we have a recitation plan this week, which would have made absolutely no sense if we didn't go through the lectures, our lectures. So once I get a link to the videos, I'll post a link, and I recommend you watch these because it's always useful to know what people are doing out there, learn about various problems and solutions and such like. So you want to broaden your horizons, right? We're done with basic MLPs, training models, the various problems with training MLPs. In the last 2 weeks, we went through convolutional neural networks. And now we are switching gears. But before that, do you have any questions from the past 5 weeks, 6 weeks? Any questions? Has everything been absolutely brilliantly clear? If I shut the course down today, everybody would get an A. Is that where we stand?
I just have a question about one basic question about padding. The padded zeros don't let the output images like we have very dark edges at the corner of the image.
So the borders are going to be, you always have problems with features at the borders. This is a standard problem, right?
So if you just use the existing values at the corner and just use like reflection.
Yeah, you can do that if you're going to have issues with derivatives, because now those features they are not artificial features. So you'd have to figure out how to pass those derivatives backwards, because they are related to other things, right? Yeah. All right. So here's a new problem. We've dealt with MLPs. We've dealt with CNNs. How to classify static data. Can you shut your laptop? Thank you. The slides are up there. So And we've seen how we can look for position or even transform invariant pattern detection. But then now let's get to a new kind of problem where we are looking at series of inputs and we want to produce an output after having considered a series of inputs. The output might be a single output to be generated when you're done analyzing the series, or you could be sequentially generating some output for every input or various things in between. The issue is we're dealing with series. So here are some problems. Speech recognition. Let's say you have the simple problem of recognizing a word in a vocabulary, keywords. You have to look at the entire input to decide what was spoken. You cannot stop halfway through and say this is the word yes. Very unlikely, right? And so you'd have to analyze the entire series of spectral vectors before taking your decision. The input is a sequence of vectors. The output is a single result. Or text analysis. This is a very common commentary on the state of the Steelers in Pittsburgh. They're always losing. But here's a bit of text. The Steelers, meanwhile, continue to struggle to make stops and defense. They've allowed an average 30 points a game and have shown no signs of improving anytime soon. Fact of life in Pittsburgh. But what game is this speaking about? How do you know? Is there any information here? Right. So the point is you'd have to take, there's no immediate cue. You'd have to analyze the entire text to decide what the subject was, right? So again, it's a sequence, a series that you're looking at before you make your final decision. Or if you're analyzing the stock market. Now the inputs are going to be a series of vectors. Maybe you're looking at all the stock indices every single day. And based on this sequence of stock indices, you have to decide how you're going to distribute your money, what you're going to invest in, and how. And again, this decision can be at the level of a single stock. So should I invest in Apple or not? Or what should my portfolio be? So in which case, your output is not a scalar, it's a vector. But again, the problem is you're looking at a sequence of inputs. So in all of these cases, you're considering a sequence of inputs, or rather input vectors, and you're producing one or more outputs. And clearly, this can be done using neural networks, right? Before I continue, I want to clarify something about the pictures I will be using. So typically, I've been showing you neural networks with all the neurons laid face up. So if I were drawing a neural network, it'd be a series of balls and a series of balls up there. They're all connected to one another, etc. So if I were to just take that picture and begin rotating it, at a 45-degree rotation, maybe it looks like a figure to the left. If I rotate it all the way to 90 degrees and I look at it edge on, it's going to look like the figure to the right. So I'm going to use the figure to the right for my representation. Anytime you see a figure of this kind, I want you to realize that every block is actually an entire layer going into the page. And every arrow is a full connection between every neuron in the lower block and every neuron in the upper block, unless I specify otherwise. There are some cases where it may not be a full connection, right? But this is the assumption you're supposed to make. Or, for example, if I had a network of this kind, which we're looking at two vectors, so the figure to the left, I'm going to show it as the figure to the right, edgewise. And again, each square represents an entire layer of neurons. And every arrow represents a full connection. Or here's another example, right? So this is just to clarify the illustration. Now let me begin using this. Now, consider the stock market problem. I want to determine what stocks I must invest in today, which means I want to make some predictions about its values or its future values at some time, right? Or maybe, is this going up or is this going down? Whatever it is, I cannot just look at the stock values today and take the decision. These things have trends. So I must consider the stock values not just today, but also all the past values before I decide. And how can I do this? If I decide that in order to make a stock prediction on day N, the trends can be determined from the past 7 days, then this is the kind of network you'd have. The prediction on each day is going to look at the input on that day and on each of the past 6 days, right? So this is, but this is just a convolutional neural network, right? Because if you want to make a prediction, this is what you'd be doing. At each time, you're analyzing that input and a bunch of inputs in the past. Where have you dealt with this problem in your homeworks? Pardon me? One dimension, but in your homeworks? Yes. Isn't this what you did in homework 1? This was your context, right? But this is when you used context, it was just a convolutional neural network. You may not have realized it. So we began dealing with convnets before we began speaking about them. I like to sneak things up on you. Now, this in the 1D CNN case, this is also called a time delay neural network. This is a finite response system. Now, what I mean by finite response is that something that happens today is only going to affect the output for a finite number of days in the future. So here, for instance, consider the red box. Assume that some event happened on day T. So as you begin making predictions, the red box has no influence on any output in the past. It only begins influencing outputs when you actually begin using it to make predictions. It will continue to begin influencing the output, in this case for 4 days, and then on the 5th day, it no longer has any influence. So any given input has influence for a finite period of time. So the response is finite in time. This is a finite response system. Anything is going to affect the output only for a limited amount of time. So this has an issue. If I'm making stock predictions, if I just look at the past 2 days, stock values have longer trends. So maybe you want to look at the past 7 days. But then the past 7 days is likely to be insufficient to make a decent stock prediction. So what can you do? You can keep increasing the lags, right? No worries. I can keep going backwards until I think I've captured enough. No big deal. I have enough CPU. I have enough memory. If it doesn't work, I'll buy a bigger GPU. Except, if you look at the stock, what are the trends? If you plot the stock values, you find daily trends. What happened yesterday is very indicative of what's going to happen today. You have weekly trends. People go out shopping on Sundays. Companies have certain things happening in the middle of the week and so on. And every one of these, they make their announcements on Fridays. So these have trends. And then you have monthly trends. Every month, about the time where people actually get their paycheck, they go out and buy things. But then you have seasonal trends. Things happen every season. You have annual trends. What happened last Thanksgiving and the Thanksgiving before that tells me about something about what kind of market I'm going to see this Thanksgiving. So in effect, the actual amount of time that you would want to consider in making a prediction is not finite. You want to look all the way in the past, right? And something like this is clearly not going to do it. So we want an infinite response system. Something that happens today should continue to influence the output forever, hopefully with fading influence, right? Something that happens today is going to have some effect on whatever happens 3 years from now, but something that happens 2 years and 60 days from now is 360 days from now is probably more relevant, right? So you want the influence to hopefully fade with time. But that's not key here. The key is that you want everything to have some say in the entire future. So first, a poll. Set an alarm. Should be 30 seconds, but yeah. Are you getting the polls?
Second poll is not there.
Oh, wait. I thought the poll numbers were up. I had put them on the slides. Okay, what are the poll numbers, guys? Can you tell me? So I had put them on my slides. My machine crashed after I did it, and apparently it recovered without the whole numbers. So
46, 646, 647.
pole number 1 is 646, 647, and then 2 is going to be 648 till, I think there are 3, we'll check. All right, so anyone tell me what the answer to the first question is? True, right? And what about the second? Obviously. Yeah, see, I have the numbers, they're just on the wrong slide. Okay. We want infinite response systems. Now, what kind of system can have infinite response? Here's a very simple thing. Suppose the output at any time depends not only on the current input, but the past output. So yt is a function of both xt and yt minus 1. In this case, something that happens the current input is going to affect the current output, but the current output is going to affect the next output, and that output is going to affect the next output, and so on. So you're going to have influences all the way down time. And so a single input influences the output for the rest of time. This kind of network where the output goes back as input is what is called an autoregressive network. It's regressing on its own output. And this specific formalism is, the original name was nonlinear autoregressive network with exogenous inputs, meaning the input itself is external, but the rest is just coming back. And now, where does the information about the past live in this network? Yeah.
In the output?
It lives in the output, right? There's nothing inside the network itself that is carrying any information about history. It's all, you're just packing it all in Y. And so here's what the network is going to look like. So let's say at time 0, you produce a yt, and that yt is going to go back into the net, and that's going to influence the next output, and so on. And so you're going to have recursion from the output back into the net, back into the input. But then if you actually draw all the dependencies over here, this is what it looks like. So as you can see over here, if I have an input at this time, it goes up and affects this output, and so it affects this output. You can just follow the arrows, and you can see that an input at the beginning of the screen affects the output at the end of the screen. So an input has affects the output forever. This is an infinite response system. I'm going to rewrite like this, so I don't explicitly show the output going back in, but the output, whatever comes out of the output layer shown in brown is going back into the network. Right? Now, I can have other kinds of connections. Once I begin drawing things like these, I don't need to look at just the immediate past output. I could be looking at more outputs, like so. The output 2 steps back, the output 3 steps back, and so on. At the same time, nothing is stopping me from looking at past inputs as well. So this is the most generic case of a autoregressive network, which is looking at all past, at many past outputs and many past inputs. So the order would be defined as the number of past outputs, the combination of the number of past outputs, and the number of past inputs. So these networks, these nonlinear autoregressive networks, are very popular in time series prediction for predicting weather, for predicting stock markets, and alternate systems and tracking models. Now, they are particularly popular in systems which have a certain degree of randomness. For example, if I'm predicting the stock market, I'm going to make a prediction today, but my prediction today is not, regardless of what my prediction is, the output is not deterministic. It's not going to be exactly that. There's going to be some noise about it. And that's what you want going back into the network, right? And so in these weather, stock market, all of these are classic instances of situations where you have some degree of randomness. And places where they become particularly popular, language models. You're seeing them all over the place these days, yes.
So able to take care of that noise just because inherently if we feed the previous outputs in, it's effectively taking the weighted average of it.
No, the point is that when you're generating an output, you're adding some randomness into the process, right? Yeah, yes, output is like sampling, yeah.
So I said, do we feed the actual output, or do we feed the generated output back into the network?
So if I'm making a prediction 10 days into the future, there is no, it is the generated output, right?
In the case of stock market, I made a prediction today, and now after a few hours, I know that what is the actual value.
Yeah, but are you going to be making a prediction for tomorrow, or are you going to be making a prediction for next week? It all depends. So if you're taking actual values, those are inputs. If you're using predicted values, those are that is the autoregression, right? So anyway, the point here is that the memory of the past is not in the network. The memory of the past is external, right? It's in the output generated by the network, which carries all the influences of the past. Let's try to push that memory into the network itself. Now, if I want to push the memory into the network, I need to introduce an explicit memory variable whose job it is to remember the past. That's all this variable does. So you'd have some variable m, which is going to be a function at any time. The variable, the memory can be a function of many things. It can be a function of the current, and it can be a function of the previous memory, the previous output, right? The hidden states in the network, the current input. The equation is incomplete, but you get the idea, right? And this memory, actually no, because it's memory, right? The inputs in the previous time, and this memory is fed along with the current input to the network to produce its hidden state values at the current time, which are then used to generate the output. The takeaway lesson here is that we're actually introducing a variable m whose job it is to keep track of memory. How exactly it does so is something that's open for discussion. So there have been multiple models proposed for this, for how to store memory. And the simplest one, the earliest one, was by Michael Jordan, not the best basketballer, but the guy who's in Berkeley. I don't know that they're different. I met neither of them. But anyways, so now in the Knox networks, we just said that we'd be looking at the output at the previous time instant. There's nothing special about the output just at the previous time instant. You could be looking at the outputs way back in the past, but then how many outputs will you use? So here the idea was that you use a running average of the output. So the m at each time is going to be some mu times the previous memory plus the most recent output. And so the memory is just storing a running average of the outputs, and this is being fed along with the current input to the predictor. Now observe that the memory module over here has no learnable components. It's just maintaining a running average, and that's about it, right? You could expand it to actually make the running average parameters learnable, but generally it's just a running average of outputs. And again, it's not tracking variables inside the network. What it's tracking is something outside. You just introduce this memory variable. So the next obvious step is to say, why just look at the output? Let's look at what's happening inside the network. And so that gave us this thing called the Ellman network, which was by Jeffrey Ellman back in 1990, where he takes the hidden state at the current time and clones it. And so the hidden state of the network, shown in green, is the memory of the network. So to make the prediction at any given time over here, he makes a copy of the hidden state here, which is like saying I just copied over with weight 1, right? And that and the current input are used to make the next prediction. Now, this, the one distinction he made is when you're backpropagating things, you want to backpropagate to everything that affects the output. And so as far as training is concerned, because you're just making a copy of all of these blocks, you might have a bunch of inputs. And this generates a hidden state, and this is copied. And then this generates a hidden state and output, and then this is copied. And this generates a hidden state and an output, and so on. And then he would just chop it up like so. And at this point, this value, which is copied from here, is treated as just another input to the network. And so for the purposes of back propagation, this entire network becomes a batch of single column inputs because no derivative actually goes past. So if you're doing any back propagation over here, an error that you compute out here would propagate, and it would be used to compute, to update the weights of this particular connection, but then there's no derivative going further back. So they call this kind of semi-recurrent networks because you're not learning from something in the distant future. Get that?
By end state, do you mean the output of the layer of the hidden layers?
Yeah. Right. Yeah.
What is the initial value for like the conflict at
The very first thing, that could be a 0 or something, right? There's nothing in memory. So yeah.
I'm a little bit struggling to understand why feeding in the hidden layer, like just before the output, is very different than feeding the output itself back into the.
So think about the language modeling problem, right? The actual output is typically drawn from a distribution that has parameters generated by the output computed by the network. In that case, there's a sampling. It's not deterministic, right? Whereas this is deterministic.
Yeah.
Yeah.
How do you evaluate the quality of our memory?
So let's wait till the end of the lecture, then come back with a question, right? Any other questions? Yeah. Go ahead, sir.
So the purpose of cloned state is only to make sure that the derivative is even.
It's just what they did back in the day when they had those computes, right? When their computation is limited. Yes, Giovanni?
Why deterministic?
Meaning, so for a given input, and the hidden value is fixed, right? But for a given input, if there's a final sampling or some kind of drawing mechanism at the output is not deterministic, like in the case of generating language. Right? So, yeah. We're going to go there, right? So this is what was done by Ellman. This was called the Ellman network. It was a semi-recurrent network, and no gradient is backpropagated over the one link. So just the story so far in time series analysis, models might look at past inputs along with current input. And looking at a finite horizon of the past inputs gives us a convolutional network, as we know. Looking into the infinite past requires recursion. And Knox networks recurs by feeding back the output to the input and may in fact feed back a finite horizon of outputs. And these are so-called simple recurrent networks, which were the Jordan network and the Ellman network actually introduced memory units whose job it was to carry some information about the past. But they're simple because these memory units did not actually influence what happens. They have no influence on training things in the past. Now, you want to consider that now, if you have a recurrent kind of computation, something that happens now might not actually show up in the output till way into the future. So influences accumulate. And so I can have something happen now that doesn't really change the output at the next time or the next time or the next time, but 10 days into the future, something that happens now will affect the output, could affect the output. And so your training paradigm must be able to capture errors way back in the future and then work your way back and find the influences all the way at the beginning of time. And something like this will not do it. So, but yet, these were the first recurrent neural networks that were proposed back in the late 80s and early 90s. There's your second pull these numbers right. Okay, guys, Someone on Zoom, maybe you can answer both questions. Is the first question, what's the answer to the first question? Zoom?
False.
False.
Second?
True.
All right, thank you, right? So everybody gets this. This is trivial stuff. Now let's go back to our question. Why do we need to have just simple recurrence? Why not have full recurrence? Full recurrence actually allows something, errors to be backpropagated all the way to the beginning. This gives us what is called a state space model. So in a state space model, the whole idea is why clone it and why make a copy? Why not just have a direct connection, in which case your derivatives can flow backwards. But then if you look at it from a mathematical perspective, here's what the model looks like. This is something that comes straight out of control systems. The system has some hidden state, H, which is computed recursively. And so the hidden state at time t is a function of the hidden state at time t minus 1 and the input at time t. And the output is at any time is only a function of the hidden state. So ht is some function of ht minus 1 and xt, and the output is just a function of ht. Of course, for this to work, you need to define the hidden state at the very beginning of time. What is h of minus 1? That could be thought of as something fixed or a parameter that you must run to. So this is what is called a fully recurrent network, or simply we can just call it a recurrent network. So here's what the computation is going to look like. A single column looks like the figure on top. You have a hidden state coming in from the previous time, the current input, and you're computing the hidden state, and that is being used to compute the output and compute the output at that time. So the entire computation over a large sequence of inputs is going to be the figure shown at the bottom. And the thing is, in the figure shown at the bottom, every column is identical to every other column, because you're performing the same computation at each time to make the prediction at that time. The only things that have changed are the input at the time and what is stored in memory. So again, you can see that an input at time 0 affects the output forever. So this is no longer a finite response system. This is an infinite response system. If I have an input out here, if I have an input here, you can just follow the arrows, and it's going to be affecting the output at any time at all in the future. So here's a summary. You have a hidden state, which is recurrently computed, and now the memory of the past is in the hidden state. The output depends on the hidden state. The hidden state depends on the past value, the remembered value of the hidden state, and the input. And in the figure here, I've just shown a little green box for the hidden state, and I'm hiding a lot of sins in it. The hidden state itself can be arbitrarily complex. It can be many layers of a network, for instance, or something even more ugly, which we will encounter in the next class. Right? So here is one example where my hidden state is just a single hidden layer in the network. All columns are identical, and you can see that an input at time 0 affects the output forever. But if I have a network of this kind where I have two hidden layers which are recurrent, now the hidden state is actually a two-layer state. And in this particular case, the information is flowing directly and sequentially from bottom to top. Again, every column is identical to every other column. But you can have more complex things like this one. Again, this hidden state has two layers, but then you have skip connections. This still falls under the same format, right? You have a recurrent hidden state, and then you have an output. And you can have something even more ugly, right? So, but this still falls under the same formalism, that you have a recurrent hidden state, where the hidden state, which is now the union of both the green boxes at any time, is a function of the current input and the hidden state of the previous time. And the output is a function of the hidden states. It could optionally also be a function directly of the input. And in every case, an input at time 0 affects the output forever. Now, here, I've just assumed that I have recurrence over one time instant. When I have recurrence over one time instant, you have to worry about what happens at time 0. I need to specify h of minus 1. because otherwise I cannot compute the output at time 0. I can have higher order recurrence. I can have second order recurrence where the hidden state at any time looks at the hidden state of the previous time and the time before that. And in that case, again, this is what the architecture is going to look like. But now my initial values have to be specified both for h of minus 1 and h of minus 2, as many time instants as I'm looking back when I'm computing the current hidden state. The simplest models, of course, just look back at one time instant. So these are the kinds of things we will consider. But then when you actually implement these things, sometimes it's beneficial to look back over longer periods of time. And there are many theoretical reasons why they actually make more sense. But they're more complicated. So this is what you usually will implement. Now, in terms of illustration, if you looked at textbooks from the past, this is how they would draw the figures. Now, these figures are very confusing because it seems to tell you that at any time, the hidden state keeps looking at itself. It's not really doing that, right? This is a very bad way of representing the picture. What this means is that that circular arrow is basically unwrapped over time. So a figure that like this one, which shows this green arrow going from the green box, a circular arrow going from the green box back to itself, really represents this sort of recursion where the green box, the hidden state, is communicating with itself at the next time instant. Or if you have something of this kind, then this is what the figure would represent, right? Or something of this kind, again. The point is the circular arrows are basically representing recursion over time. Now let's look at what the math behind this particular model is. Let's consider the simple case where I just have one hidden state and it's recurrent. So I'm calling it recurrent because it's feeding back on itself, right? So in a recurrent model of this kind, the hidden state, there's one hidden layer. So the hidden state at any time is the h of minus 1, of course, must be specified or is a learnable parameter. So this guy is part of the network. It's something that you don't have. That you don't compute. But for the rest of these, you have an activation which applies on an affine function of all of the inputs at that time. So it's an affine function of all of the inputs at that time and all of the hidden values at the previous time. So this is an affine function of xt and h of t minus 1. And the hidden value is an activation which applies to this affine function. The output is simply an activation, typically a softmax, which is applied to an affine function of the hidden state. So over here, you're simply going to get f, which applies to an affine function of h of t. Right? Now, when you write this out with explicit summation, it looks ugly. It's more convenient to write it in matrix vector format. And so the hidden state in this case is an activation function which applies to a weighted sum of the input. The hidden state at time t is a weighted sum of the input at time t, the hidden state at time t minus 1, and a bias. And the output y is an activation f2 that applies on a weighted function of the hidden state and the bias. Now observe that there are two different kinds of weights over here. These are what I'm calling current weights. These are weights that apply only to vertical arrows. And then you have recurrent weights, where they refer to values at the previous time instant. So the superscript W11 and W11 means that it's a recurrent weight which comes from the first layer at the previous time to the first layer at the current time. And the superscript just W1 says its weights going from the 0th layer up to the first layer. So in the second case, again, you only have current weights, right? So it's W2, meaning these are weights going into the second layer and the corresponding bias. So this clear to everybody so far? Now, here's a slightly more complex model. In this case, I have two hidden layers, two recurrent hidden layers in my network. So the first hidden layer is value is computed by applying an activation to an affine function of the current input and the hidden states of the previous time. So H1 has this activation applied to some weighted combination of the x's and a different weighted combination of the H1 at the previous time. H2 now has an activation that applies to a weighted combination of H1, the first layer hidden state, and H2 at the previous time. And the output Y, of course, is just an activation that's applied to a weighted combination of the second hidden layer. So you want to go out and wash your face or something? Do you want to go out and wash your face? Are you sure? Okay. I too fall asleep. It's okay. Try to stay up. Anyway, there's coffee outside. So this clear to everybody? Yeah. Now, typically, the activation functions for the hidden states tend to be tan H's. And for the output, they tend to be softmaxes. Why tan H's and why softmax? Softmax, we all know. Why tan H's, we will see in a couple of classes. Yeah, Dennis.
Professor, what's the value of J here? The one that goes from 1 to m?
Let me fix that for you. Okay. So if I write it in vector format, it's easier, right?
Yeah, a lot.
The K is gone.
Okay. Magic.
Yes. You ask me a tough questions, I make it go away.
I literally don't understand linear algebra.
You literally understand linear algebra and don't understand the simple stuff.
Yes, sorry.
You've got it backwards. The more complex it is, the better CMU students understand it. It's one of the problems of being too smart. But anyways, so this is basically what we had, right? Again, H1 is works on an affine combination of the current input and H1 in the previous step. So it's some W1x, this is the current weight, times W11 H1 of t minus 1, which is the recurrent weight. Similarly, H2 is W2 of H, which is the weight of this connection, W2 of H times H1 plus W22 times H2, which is the recurrent connection. And the output Y is simply going to be W3, which is this weight times H2, right? Plus the bias. So you see how this works. It's very simple, yeah.
Professor, so here now W11 and W22 are learnable weights for the...
All W's are learnable.
Yeah, so earlier when you gave the example of a simple like running average, there you said that we can do something complex like expanding it out and learning the weights for running average. It's something similar here, right?
So the running average was when you had that was for the Jordan networks, right?
Which networks?
That was for the Jordan networks very actually. So yes, the weights with which you compute the running average can be learned, but we aren't going to revisit Jordan networks. We're 20 years out of date, yeah.
So are there weights for h of 1 minus 1 and h of 2 minus 1?
So the same weight applies, right? This again, this is a very symmetric network. So this weight is the same as this weight, is the same as this weight, is the same as this weight, is the same as this weight. What this value is, you could set it to 0 or you could learn it. Okay. And more of the same ugly math, right? But basically you get an idea of how to write these things. Any questions? So now there are many variants to this basic model. Here I'm just showing you in all of these figures, I showed you a very specific kind of computation that, obviously I'm targeting the stock market. So at each time you got an input, you had some recurrent values, and then you made a prediction at each time. So you're synchronously producing an output for every single input. This is not the only way of doing things. There are many variants. So here, the first figure shows a conventional MLP. There is no recurrence. You don't see any loopy arrows. And an input produces a single output. You can actually use conventional MLPs to analyze series data by just using the same MLP on every input, but you're sort of losing the fact that the data are time series. You can have models of this kind where a single input generates many outputs. So this is the same thing as before, except there are no inputs at the future times. Can you give me an example of where this might work? Yeah.
Language model?
Language models, I can give it a seed. If you're using ChatGPT, they're doing something very similar to this. Or image captioning, the single input could be features derived from an image, and then it's generating the entire caption thereafter, things like that. Or here's another one. You look at an entire sequence of inputs and then produce a single output. So this could be sentiment analysis. You have to read the entire text and determine the sentiment. Or speech recognition. You have to look at, when you're doing isolated word recognition, you have to look at the entire input and then decide what the word or sound was. You can also have models of this kind, where you analyze the entire input and then produce the entire output. This you would use, for example, if you were performing machine translation, because there's really no one-to-one correspondence between words in English and words in German. In English, the verb occurs in the middle of the sentence. In German, you have to wait all the way to the end of the sentence before you find out if A patted B or A punched B, right? So the orders. So you can't just be sequentially generating output. You have to analyze the entire input and then generate the entire output. Or, of course, the simplest case is the one to the extreme right, which is what we've been looking at. And now it turns out that if you figure out how to do this thing to the extreme right, you cover most cases. So we're going to sort of focus on that last one for the most bit. So here's the story so far. We're just adding 2 more bullets. State space models retain information about the past through recurrent hidden states. These are what are called fully recurrent networks. The initial values of the hidden states must be specified, and they might be learnable parameters also. And state space parameters, state space models have this characteristic that an input now affects the output all the way into the future, which means that if you have the kind of behavior where an input at time t triggers some changes in the output at t plus 1000, that influence can be carried back to learn how this can happen. So we've defined the network. Any questions? None. How do we train the network? This training the network is what we call back propagation through time. Why would we call it back propagation through time? Anybody want to guess?
Moving through time. Back and through time.
So you are back propagating, right? If you think about this, this is like having, I've just drawn it left to right. I could have drawn it vertically, could I not? And so you'd be back propagating from the top to the bottom. The top is at the final time, the bottom is at the initial time. So when the gradients are flowing backwards, they're actually flowing backwards through time. So it's called BPTT, or back propagation through time. Training is very similar to standard training. You're going to be given training data input-output pairs, where you have an input, but now the input is going to be a sequence. Again, remember, I'm going to focus on this model here for now, right? So the input was a sequence, and the output is a desired output sequence. So at each time, what must the output of the network be? And so given a collection of these XT pairs, I have to train the network. Now, if I just unroll the computation, right, this is what the computation is going to be. Every column is identical to every other column. Once again, just remember this. And so when I'm training the network, as before, we're going to have to do a forward pass, and then you're going to have to do a backward pass. So the forward pass, again, in the forward pass, you'd be computing the outputs at each time. Then you'd be computing a loss, and then you'd be computing the gradients. How much does changing any parameter change this loss? And then you'd be using gradient descent to train the network. But this is no different from training a standard MLP, with one caveat. This is just a giant MLP, right? Once I draw it like this, there's nothing. If I could have just drawn it vertically rather than horizontally, I could have rearranged the arrows, it would look like an MLP. What makes this special is that every column is identical to every other column. So this is a giant MLP with shared parameters. And that's something that we have to deal with. So in the forward pass, we just pass the entire sequence through the network and generate output. So you'd have something of this kind. I'm assuming that you just have one hidden layer. Do I? Actually, no. So you'd be initializing your, I can call these the 0th layer, right? And so at each time, as I start from the beginning, the initial value is just the 0th layer is just the input. Then I loop through the layers, and at each layer, I compute an affine value, which is a recurrent function of the hidden state at the previous time, and a current function of, actually a recurrent function of the previous hidden state at the previous time, a current function of the hidden state at the current time, but the lower layer, and the input itself. And well, actually the input is right here. So it's just a recurrent function of the hidden state at the previous time and a current function of the hidden state at the lower layer at the current time. And then the H is computed by applying an activation to Z, right? So you're just looping through the layers. And then once you get to the output layer, you can compute your affine value once again and apply an activation to it. The code is very simple, nothing particularly complicated. But now, having done this, you would have passed your entire sequence of inputs in. Figures are better than code. You'd have passed your entire sequence of inputs in, and you'd have computed an output at every time. And then we have to define a loss. And then the derivatives of this loss must be backpropagated. I'm going to redraw the figure like this, just so you know, it's kind of clearer. All inputs are going in at the bottom of the box, and all outputs are coming out of the top of the box. So the curled arrows kind of make sure that you don't get this wrong impression that there are two different outputs coming out of the green box. That's all. The first thing we need to do to train is to define a divergence function, a loss. And this is the divergence function between what and what? Pardon me? What would you think it is for any network? Yeah, where Denise?
I mean, is this a trick question?
It's not a trick question. It's a straight up question, right? After 6 weeks, you must be able to answer me.
So it's the difference between the predicted and the actual output by and the average, and its average.
So here is the key pitch. It's a partially a trick question. It's
You lied.
I like to lie, but anyway, it's a divergence between the sequence of desired outputs and the sequence of actual outputs. So the answers you gave me about computing the divergence at each time and summing them up and so on, they're just a special instance. But the real thing is that the network is generating an entire sequence of outputs, and there's an entire sequence of outputs that you expect it to generate. And so the divergence is actually specified between these two sequences. This is not the sum of the divergences at individual times. That making sense to you guys, right? You are doing sequence prediction after all, right? You have to deal with sequences. And this, you can explicitly define it as the sum of the divergences at individual times, and we'll do it. But there are many cases where you cannot do so. And this actually causes us a lot of grief, and much of what we will discuss in the next week, next couple of weeks, has to do with how you deal with situations where divergences are not simply defined on a time instant by time instant basis. So here's my notation. I'm going to say that yt is the output at time t, right? And in this particular example, I'm just using this picture for illustration. So I've introduced the various variables. You have one hidden state and one output state. So the affine value at the first hidden state is shown as z with superscript 1. The output of the hidden state is shown as h. The affine value at the second layer, which is the output layer, is shown as z with superscript 2. And the output is y. Output of the second layer is y, okay? And now let me also introduce the various other variables. W superscript 1 is the set of weights from the input to the first hidden layer. W superscript 2 is the set of weights from the hidden layer to the output. And W superscript 1 is the set of weights associated with a curvy arrow, which is the recurrent connection, right? So now as always, when you perform back propagation, the first thing you want to do is to compute the divergence, derivative of the divergence with respect to the output of the network. But here, you have to start at the end of time, because that's where the final output happens, right? So the first thing you need is the derivative of the divergence with respect to the final output. So once again, here's the key bit. The divergence that you compute is the divergence between two sequences, between the sequence of actual outputs and the sequence of desired outputs. But nonetheless, for us to be able to train the network, it is critical for this divergence to be differentiable with the output at every single time. So we need to define our divergence so that it accurately captures the sequence relationships, and at the same time, I can compute the derivative of the divergence with respect to the output at each time. If I cannot do this, then obviously training is not going to happen. So this is a challenge. But for now, we're going to assume that this is feasible, right? And I'm going to specifically assume, for convenience, because this is an assumption that we often use, is that the divergence, the sequence divergence is actually a sum of divergences at individual times, that you can compare the output at each time with the corresponding desired output at that time. And that divergence, you can sum these divergences over all time, and that's your total divergence. This is an assumption. It's not always valid. And now, once I define it this way, I can compute the derivative of the divergence with respect to every one of the outputs, right? It's just the derivative of the local divergence at that time. So the derivative of the total divergence with respect to yt is the derivative of the divergence at time t with respect to yt. So problem solved. So assuming this, I can now claim that I have computed this term, which is the derivative of the total divergence with respect to the output of the network at the final time. So now if you're doing back propagation, what's the next thing you would compute? Yeah. What would it be, guys?
The perturbation that is caused at the previous edge that influences.
So that's way back when, right? So what is the first step? You're going to compute the derivative right there, are you not? The derivative with respect to zt. And so the derivative with respect to the zt is going to be the derivative of the divergence with respect to z2 of t is going to be the derivative of the divergence with respect to y of t times the derivative of y of t with respect to z2 of t. And this, of course, is the Jacobian of the activation, right? Just straight up. What's the next thing you would compute? Going back. Someone, guys, someone at the back. What is the, or on Zoom, what is the next thing you would compute? Kofi, what's the next thing you'd compute? You're performing back propagation, guys, help me.
Weights and
so what is the derivative with respect to?
The derivative with respect to W11
is, what is that? Can someone tell me? At this point in the semester, you must be able to just tell me this stuff with closed eyes, right? You've done homework 1 and part of homework 2.
Derivative with respect to z prime.
It's going to be, I want the derivative, I've computed the derivative out here. There are 2 more derivatives to compute. One is the derivative with respect to this term, correct? And then there's the derivative with respect to this weight. What is the derivative with respect to this term here?
it's the derivative with respect to divergence multiplied by the weights and then conversely multiplied by.
So the next thing you do is the derivative with respect to, say, h, right, at t is going to be the derivative of the divergence with respect to z2 at t, right, times w2. This is what we've seen, correct? Straight up. What is the derivative with respect to these weights? What is the derivative with respect to these weights? Yeah.
dz, like the derivative with respect to d is z, but then we're going to be multiplying it with every respective activation for like specific weight that influences.
So what is that?
That was a really bad way of phrasing it.
That
It
is
is.
yt minus 1 or zt minus 1.
That you guys, come on, help me, please. I'm stuck. I've forgotten. H. Thank you. So where will that H go? Is this a column vector or a row vector in our notation?
Row vector.
Row vector. How many of you think it's a row vector? Raise your hands. How many of you think it's a row vector?
So Jacobian.
Yeah, so I'm assuming column vector notation. What is the derivative of the divergence with respect to z? Please. Is it a row vector or a column vector? If z is a column vector, what's the derivative of the divergence with respect to z?
Row.
Can everybody say row together, please? Right? I didn't hear it. Say it. 1, 2, 3. Row. Thank you. Right? And so what is the derivative? So can I just multiply that by h and will it give me a matrix?
H transpose.
It's going to give you a scalar, right? It would have to be h times. So what we saw was this. We said h times this guy. This is a row vector. This is a column vector. That's going to give you a matrix. Correct? Do you remember this? Please raise your hands if you remember this. So I know that I'm lost you. Most of you don't remember this. Raise your hands if you don't remember it. And those of you who didn't raise your hands, why didn't you raise your hands? You lady there, you didn't raise your hands. Yeah. Yeah. Do you remember it or do you not? Okay, let me try this again. Do you remember this? Raise your hands if you do. Oh man, this is the most dispirited class I've ever been in. You don't know and you don't know. This is Zen, right? Quantum deep learning. Anyway, so but yeah, we know how to compute the derivative with respect to the weight, right? So that's what you're going to do. The next thing you would do is the derivative with respect to h is simply going to be multiplying the derivative with respect to z by the weight. We just saw this. And the derivative with respect to the weight is h times the derivative with respect to z. And all the sizes must work. Okay, what is the next thing you're going to compute?
The input.
Pardon me? But even before that, can you directly compute the derivative of the recurrent weight?
The derivative before the activation.
Yeah, you would need the derivative right there, correct? You're going back there. That's the derivative with respect to z1. Can someone give me the formula for that without looking at the slide? Marlies is giving me that, very scared. She's trying to hide her face. What is that? What is the answer?
To what are we now? With respect to what?
I want the derivative with respect to the input to the green box. What would that be?
The derivatives of before times with respect to the z.
Yeah, so what was that? It's on the slides, guys. Okay, it's a derivative with respect to h, which is the output of the activation, times the
Activation with respect to.
So what is that?
That is the point.
That is the Jacobian, right? Of the activation, is it not? And so you would get the derivative with respect to z. That's ring a bell? Okay.
And this Jacobian will again be a row vector, right?
The Jacobian is a matrix. Yes. Okay. A row vector multiplying by a matrix is going to give you a row vector. The Jacobian is always a matrix. Please. I've lost you guys at some point. Now, once I've got the derivative with respect to z, what is the next thing I would compute? Yeah. Go ahead, Denise.
It's like there's two things now, right? The weight that comes from the return from like the previous units and the weight that comes from the input.
Okay, and what will this formula be?
Okay, so So for the weight, I think the formula is gonna be, we multiply, okay, let's call this value Z1 T minus one, right? Z1 T minus one multiplied with.
It's H, not Z, because it's looking at the output of the activation.
Yes, sorry. H1 T minus one multiplied with the derivative of, like the Jacobian or.
Not the derivative for Z, right?
Yes,
Okay,
for
thank
Z1,
you.
yes. And I don't know if that's a row vector or a column vector.
It's got,
I'll get it out.
again, the derivative with respect to Z, is that a row or a column?
I think it's a row vector because we said it.
If Z is a column vector, we said that the derivatives are transposes of the.
Yeah, it's a row vector.
It's a row vector, right? And so that's why the result is going to be a matrix. And so indeed, I want to compute the derivative with respect to this weight, which is the input times the derivative with respect to Z, and with respect to this weight, which is the hidden value at time t minus 1 times the derivative with respect to Z, right? Everybody with me so far? At least I hope you are. Okay, let's try this. Can you say yes together? Yes. Okay. Most of you just laughed. Okay, yeah, coffee. Z is the affine value that goes into the activation. All right. Yeah. Any other questions? Yeah.
Why if like the derivative of V like H with respect to V at a Jacobian measure, like we have multiple.
That's an activation function.
But
Right.
even activation function like why we are not taking an element-wise product?
The element-wise product is the Jacobian of an activation where it's an element-wise computation is just a diagonal, right? So it will be an element-wise product in the actual computation. Yeah.
So the Z is the output of the activation.
Z is the affine value, yes.
And what is the after the activation? What position are you?
So after the activation, we call it the hidden value H.
Okay, so that becomes it. Okay, cool.
Correct. Okay, so everybody with me. So this was the easy part. Now help me with the difficult part, right? What is the next thing I would do? I'd take a step back.
Derivative for HT minus 1.
So the first thing I'm going to say is I have a derivative for of the divergence with respect to yt minus 1 right there. And then I'm going to assume that I can compute the derivative at z2t, right? Which is the derivative at yt minus 1 times the Jacobian of the activation at t minus 1. And then I can use the same formula as before, but now observe this, that the output of the hidden state at time t minus 1 went to two places. One went up, one went right, right? So if I perturb it, two different things are going to be perturbed. So I need to compute the derivative along both sides. And so therefore, this derivative with respect to the derivative of the divergence with respect to this h is going to be the sum of the derivative here, which is the derivative of z2 at t minus 1 times this weight, and the derivative along this path, which is the derivative out here with respect to the derivative of z, the recurrent z at t times the recurrent weight. That makes sense to everybody?
Yes.
Blank face, any blank faces? Yes, there's some blank faces. That makes sense to you? Okay, can I have a little more enthusiasm when you nod your head? Right, okay. So, yeah. Go ahead.
Did you say at this point that the connection share the weights between the time are like shared or like?
Because every column is identical to every other column, but we have not yet come to that derivative, right? So here's the next thing. This is h is going to two places, which is why you have the derivatives coming back. I mean, if I have a variable, you have an influence of this kind, right? My influence here looks like so. This is, I'm way behind time, guys, but still. I have h of t minus 1 is affecting z at time t, and this is z1 at time t and z2 at time t minus 1. Both of them affect the divergence, correct? So I have to compute the derivative of the divergence with respect to, that's the next time, right? So this is the figure at the next column, and this is the z in the same column directly above it. That's why you have two derivatives being added.
Wait, so are the weights, I remember you saying some time before that the weights on the straightly line is the same at all time
Okay,
steps?
thank you. So let's go back to that. If I want the derivative with respect to the weight on the red arrow, that's going to be the h just before the weight times the derivative with respect to the z after the weight, right? That's how we said it. But that would be the derivative that you computed just here. So I can compute the derivative here as this h times the derivative for this value. But since this weight is the same as this weight, I have previously already computed a derivative for that vertical arrow, right? I just sum them up. That making sense? Right? And so then I can use that and go back. Now that I have the derivative for that weight, I can follow the same chain rule, compute the derivative with respect to the affine value for the hidden state. And then when I compute the derivative for this weight, again, it's going to be xt minus 1 times the derivative for z1 at t minus 1. But that, because that arrow is the same as has the same parameters as the arrow at the next time, I'm doing a plus equals, as you see in the code. I'm not just computing an independent set of weights. Did that at all answer your question?
Wait, so they're different because you're accumulating.
Yeah, the weights are the same. The derivatives are being accumulated, right? Right? And so also, if I go back here, I can compute the derivative for this recurrent connection, which is going to be now ht minus 2 times the derivative for zt minus 1. But that is going to be added to the derivative that I had previously computed because they have the same value. And so I can note the addition, right? In every case, I've written the scalar version and the vector version of the equation. You're just accumulating the derivatives. And I can keep doing that and continue all the way back to the beginning of time. And eventually, I can also compute the derivative for h of minus 1. Yes?
Ideally, we wanted our infinite network to grow weaker over time.
These are derivatives, right? He's just saying that all of these, they're shared parameters. So all of these derivatives must be added up. That's all, right? I mean, the influence grows weaker over time, but then you also have outputs at other times, right? Yeah.
But like for the weights, if they're the same, like when like during back propagation, would they update those differently, different gradients, so when the weights change?
Pardon me?
So you mentioned the weights are the same, right? But then like when you back propagate, like if the gradients are different, wouldn't they like the weights be different?
The gradients are not. So think about this. If I give you two training instances in a mini batch, they're both using the same sets of parameters, are they not, in the network?
Yeah.
Do they get the same derivatives? Every column has a different input, right? And a different output. Yeah. Okay.
So if the derivatives are summed up, that means like the derivatives at the end are very big, right? If it's like
They're not necessarily very big, but you're right. You have a point.
it's like vanishing or exploding.
We'll cover that. That's a good point. Okay. So.
That is very nice.
Yeah. Any other questions? No. I'm running out of time, so yes. No questions. If you haven't understood it, you're lost. But here's the complete set of equations. I've tried. Right? So this is the complete set of equations. You're going to work your way backwards through time. At each time, you would compute the derivative of the divergence with respect to yt. This you assume is given, right? This is from the definition of the derivative. You can multiply that by the Jacobian of the output activation to get the derivative for the affine value at the output layer. Then from that, you can multiply that by the weight, vertical weight, and you can multiply that so you'd compute the derivative here as this derivative times this weight plus this derivative times this weight, right? And then you can work your way down and then compute the derivative with respect to here. And then subsequently, you're going to be computing the derivatives for each of the weight matrices and accumulating the derivatives. The equations are all on the slide. We won't go over it. And I have code, right? But I won't show you the code. This can be generalized to pretty much any architecture. The concept is very simple. There's nothing particularly complicated. The only two requirements are A, you must be awake in class, and B, you must just follow the regular math and make sure that you're accumulating things that must be accumulated, right? There's nothing more complicated than a matrix multiplication anywhere in the whole process. So that's all it really takes. There's a poll. I'm going to run a few minutes over, and that's because you guys didn't answer my questions. So I blame you. Okay, time's up. All right, guys. Someone on Zoom, the first statement. First question, right or wrong?
Wrong.
False.
And what about the second one? Second question. Is the first statement true?
No.
Second one.
Yes.
Yes.
Thank you, right? So, and I'm going to pick one of you here at random for the next poll. Be afraid. All right. So, anyway, that's the basic idea of a recurrent network, how it works. And you can have some very simple extensions. Now, and this is this notion of bidirectionality. There are many problems where the input is not merely sequential, but you actually have the entire input sequence. It's not arriving one step at a time. And you have to analyze the entire input sequence and make predictions about every single input in the sequence. In this case, you can take advantage of the information that's present in the future, and this will be relevant. For example, if you're doing part-of-speech tagging, then the part-of-speech tag for any word depends not only on the words that occurred before it, but also on the words that occur after it. And so you want to be able to look at both things. But then, how do you compute something where information is flowing both ways? That becomes challenging, right? Because something in the future affects the present, something in the present affects the future. This seems kind of broken. So the way we deal with it is by breaking it up into two steps. One is a forward recursion, and the other is a backward recursion. So here's what we will do. We're going to have a block where within a block there are two distinct kinds of recurrences. One that goes from the beginning of time all the way to the end of time. Here h of minus 1 must be specified, right? The other, which starts at the end and recurses backwards through time. Here h of infinity, which is the initial value of after the end of the sequence, must be specified. And these are going to be two different sets of weights. The weights for the forward recursion are very different from the weights for the backward recursion. So within any block, what we would do is get an input. The same input is going to be applied for forward recursion and for backward recursion. Each of them is going to generate their own output. And now if I have an input x, which goes into a forward recursion, and it also goes into my backward recursion. Each of them is going to generate some vector of outputs, and I can just concatenate these two together. And so I've captured both of them into an extended vector. Yeah.
Professor, would this be impossible if there was a direct connection between the backwards and the forward? Like in that case, between HF and HB at a specific time?
You cannot, because then you'd have.
Then you cannot form a block, right?
Yeah, because there's looping, right?
Okay, yeah.
So that's why you have to break it up. But is the computation kind of making sense? I have a forward computation, I have a backward computation, and at each time I just attach the two outputs to generate the final output. Is it right?
Is the X different for the forward and backward?
No, it's the same input, right? I'm just saying that I have the sequence of inputs. For example, I give you a sequence of words. I need the part-of-speech tag for the 7th word, right? It's the same sequence of inputs. They're not different. Yeah.
Professor, you earlier specified that initially at the start of the network, the first block is 0. Now this is a bidirectional.
So here you need an initial value h infinity, right? That's shown in the figure. The two blue blocks must be specified. Okay, all right. And then the rest of the connection is easy, right? So here's what you do. In the forward connection, forward pass, you take the input and run through the recurrence here from the beginning to the end. In the backward pass, you run through the recurrence from the end to the beginning, and then just concatenate the two. You patch the two. You can sum them up. You can concatenate them up. You can have any kind of operation that combines the forward and backward predictions to come up with your final prediction. The simplest thing to do is to just concatenate the two so you don't lose any information. And then you can attach these blocks any which how. So you'd have a bidirectional block within your network, which is which is no different at a meta level from a unidirectional block. And so you can have this larger network. This making sense to everybody? Right. So yeah.
Will it make sense with the large text because the text have the structure, text have a syntactic structure flowing from forward to backward, but if we start computing the reverse.
Here's the thing. What happens? The syntax. When I look at an "and," I know that what follows must be an apple, right? If I look at an apple, I know that what preceded it must have been an "and," not an "a." So if there's information going forward, there's information going backwards, right? So, but in general, in many cases, this works. And there's a final poll, and then I'm going to go over by 2 minutes. I have no choice. Sister, yeah, only 15 seconds for this one. Okay, Marlies, yes or no? Why not? You cannot see the future. So you cannot use bidirectional networks because you cannot see the future, right? But then, how would you perform back propagation over here? I'm going to skip the code. The way you would actually write the code is you just write the forward code, and the input can be flipped. And then you can use the forward code to compute the backward computation as well, and then flip the output. So in terms of code, this actually doesn't make things very much more complex. But then how about back propagation? How does that work? So here is what happens. Very simply, I'm going to go through this really quickly. Let's say I have this bidirectional layer. So this is my forward layer. This is my backward layer. At any time, this guy is going to give me a vector. This guy gives me a vector. And so the output of this block is the concatenation of these two vectors, right? And the same input is being passed to both. So this input influences both blocks. When I compute my derivatives backward, I'm going to get both portions, derivatives for both blocks. I can use the derivatives for the upper block. So I can use these derivatives and perform back propagation from the end to the beginning for the upper block. And then I can use these derivatives, which correspond to the output of this block. And here I'm going to be performing my back, I'm calling it back propagation, but back is in the sense of the direction of computation. So the derivatives will be going from the beginning to the end. Both of these, I just use a standard derivative computation, but in the end, both of them are going to give me derivatives with respect to the input x. I'm going to get one derivative from here, the other from here. What do I do with those? Pardon me? Concatenate. I have to sum them. The same x is influencing the divergence in two different ways, right? And so you can just sum them up. X is being used for the forward computation, which affects the divergence. It's being used for the backward computation, which affects the divergence. So you get derivatives down both paths, and they must be summed up. And I have some pseudocode here. I'll skip this. So training recurrent networks requires defining a divergence between the actual and desired output sequences, back propagating gradients over the back propagation requires back propagating gradients over the entire chain of recursion, and pooling gradients for parameters. Bidirectional networks analyze data both ways, beginning to end and end to beginning. In this case, backprop must follow the chain of recursion separately, the forward and backward nets. We'll stop right here, and we'll pick up in the next class with some of the challenges with trying to train these networks.